Yes, I welcome you all for another beautiful presentation on random variables, right? So, in the last presentation, we have started this random variables and then random processes subject actually, and we have seen brief introduction about random variable, right? So let me explain you once again for your clear understanding, right? By the way, today it is the lecture number 2, right? This is lecture number 2 we are going to see. This is the lecture number 2 in which we are going to see again some more information on the random variables, and in which the main topic is random variables, and again under the subtopic is probability distribution function, that is denoted by capital PDF, or also called as cumulative distribution function, CDF, right? So this particular PDF or probability distribution function can also be called as cumulative distribution function. This is what today I am going to cover in today's presentation. And before going to discuss about this particular PDF or CDF, let me explain you once again about the brief review of this random variable, right? What is a random variable? Already we have seen the very nice definition of a random variable in the last presentation. I will explain you one more time for your better understanding. Okay, so let us recall that in the last presentation just we have seen one a sample space actually. Let us you can okay, let us say you have some samples on sample space. This is what we are calling as sample space, right? So this is denoted by capital S normally, and this sample space is, I mean, defining certain experiment on this sample space. This sample space is defining certain experiment, and for that particular experiment, the number of possible outcome values of each iterations are denoted by like this. I mean, x1, x2, x3, x4, and so on. So for all these things, actually different, I mean, outputs, outcome values of the experiment, which was decided by the sample space. Now, now I am introducing a variable. That variable I am introducing now. Do not confuse here. I am not introducing. I am not talking about either yes or small x1, x2, x3. No, I am introducing a new variable. New means other than s and then these x1, x2, x3. I am defining or introducing one variable. I am naming it as a random variable, and I am denoting that as a capital X actually. I am denoting it as a capital X, which I am calling it as a random variable. I am calling this particular variable as a random variable. A new variable I am introducing now in order to bring a relationship between the sample space to a real number, to a real number, to a real number. Real number is nothing but that real number is associated with this number of possible outcome values actually, right? Or otherwise you can say that this capital X, the random variable, is nothing but it is a real valued function. Okay, so it is a real valued function. It is a real valued function, or otherwise you can say that it can be a rule. It can be a rule or function, whatever it is. it can be a rule, or it is a real valued function, and that maps between the sample space to the each outcome value of the sample space to a real number. That is what the a definition of a random variable. Now here different outputs are there, like x1, x2, x3, x4. All are associated with one particular, let us variable or number, you can say. I am calling it as some x. Therefore, in this way, what I mean to say is that the random variable which I am defining now is denoted by capital X, and its a possible outcome value are represented by small case letter x. Remember that the random variables are denoted by capital letters like x, y, z, capital X, Y, Z. Already I have explained this in the last presentation. X, Y, Z, and the possible outcome values of each X, Y, Z are denoted by corresponding smaller letters, right? And now the important thing is that now if you define the subset of the sample space, the subset is nothing but x is less than or equal to x. If you write like this, it is nothing but it is a subset of the sample space. If you write like this something, okay, in that bracket form, then that is called a subset actually, right? That is called as a subset. If you write a subset, right, that is what capital X is less than or equal to small x. If you write like this, it is a subset basically. It is a subset of sample space S. And this subset is called as an event. This particular subset is called as an event. This is called an event, right? And if you take the probability of the subset, that is nothing but probability of capital X is less than or equal to small x, then this is called a function. That is what our distribution function. This is what we have seen in the last presentation. Now we are considering a sample space, is it not? We are considering a sample space. In that sample space also, so many elements or possible outcome values of particular experiment which is defined by the sample space is there, and we are mapping actually sample space to the each outcome value in a form of or in such a way that it should represent a real number. So in order to give a relationship for that mapping, for that I am using a variable. That is what a random variable. Remember that random variable never depends on time. No, it is a number basically. The random variable is a number, is it not? It is a number. It will not depends on time. No, right? So it is a number actually. It is a function. Otherwise, it is a real valued function. Okay, that gives a number, possible outcome value. That is what. So you are performing certain experiment, let us say tossing of a coin, say for example. In the experiment of tossing a coin is an experiment, is it not? Tossing a coin is an experiment. So what are the possible outcomes? So in the tossing of a coin, you have either head or tail. There are two outcomes, maybe possible outcomes are there. Either you will get either head or tail, is it not? Either head or tail. These are the two numbers, not time. Here it is not the time there. It is a number, either head or tail, right? That is one experiment. And coming to the next experiment, throwing a die. So the die will have 6 faces, is it not? The die will have 6 faces. 1, 2, 3, 4, 5, 6. 6 faces will be there, or 6 numbers you can say. 1, 2, 3, 4, 5, 6. 6 numbers will be there. right? So therefore, in each iteration, you will get certain number. You means if you define that, you have to define that which number you want to expect, which number you want to be, happen, either 1 or 3 or 6, whatever it is. That is what. So clear. So this is what actually. So the sample space contains how many possible values? What is the experiment? Is it not? Depending on the experiment, depending on that possible outcome values, right? I am relating these two with a with a function. That function is a random variable. Clear? And now I am defining a subset that this is my random variable. This is a real number actually. Real number. And my random variable must be less than that real number. Real number. Then this is called an event. This is called an event. If you take the probability of that event, then that is called a distribution function or PDF, probability distribution function, or otherwise also called as cumulative distribution function of random variable x. This is all about a single random variable. And further we can see about the multiple random variables also. Then the same concept will little bit extended. Right? This is what the definition of a distribution function. This is the simple definition. Therefore, whenever you will be asked in examination, you must note down this expression of for distribution function. You must note down. This is the expression for probability distribution function, are also called as cumulative distribution function. Clear? So we have few important properties actually. I will explain you that. Okay, I think all these are useful for your for solving the problem actually, right? So here proofs are not required because you must know the properties actually. What are the properties? So properties. Properties of, I can write PDF, capital letters. PDF are also called as CDF, cumulative distribution function, and that is nothing but, it always remember capital F of suffix capital X into bracket small x. This means it is the distribution function. Representation of the function is with capital F, means PDF or CDF, and this capital X identifies, gives the random variable x, and where bracket small x is nothing but the possible value of that random variable x, right? Let us see, there are a few important properties are there, those we will see now. The first property, right? The first property, what is the first property? You know, the first property of this probability distribution function is nothing but, so the f of x minus infinite equal to 0, means that the number, the real number, whichever we are considering the number, see that this x is defined over minus infinity to plus infinity, let us say plus infinite. Then, right, whatever the number we are taking, that small x is defined over minus infinity to plus infinity. Then at this particular value of infinity, what is the distribution function? That is what this. At x equal to minus infinity, what is the distribution function value? It is 0. That is the property. So the distribution function at x equal to minus infinity, it is 0. Similarly, what is the distribution f of x value at x equal to plus infinite? That is your second property. So second property is nothing but f x of this is plus infinite. What is the distribution function at small x equal to plus infinite? It is 1. It is 1. Therefore, at x equal to plus infinity, the distribution becomes 1, whereas at x equal to minus infinity, the distribution becomes 0. These are the two. And whereas the third property, it is nothing but the combination of property number 1 and then property number 2. That is nothing but, so the limits of the distribution function lies between 0 is less than or equal to f of x of small x is less than or equal to 1. If you combine these two properties, so you can write like this. This is the combination of first two properties gives rise the third property, right? And then there is another property is also there, that is called the property number 4. Let us see the fourth property of your distribution function. The fourth property gives that, let us say for example, if there are two possible outcome values of small x, nothing, that is x1 and x2. Let us say x1 and x2 are there, two possible outcome values of small x. Then if that x1 is less than x2, let us say if x1, x2, these two are the possible outcome values of small x, and say that or assume that x1 is less than x2, then correspondingly what will happen to the distribution function? What will happen to the distribution function? So the distribution function at x1 gives the rate f of x1 is same less than f of x2. Very simple actually. So if the possible values are in this way, means x1 is less than x2, correspondingly the same will be valid for the distribution also. fx of x1 is less than fx of x2. As x1 is less than x2, correspondingly fx of x1 is less than fx of x2. It indicates that the distribution function is a non-decreasing function. For this it is called as non-decreasing function. Clear? Non-decreasing function means what actually? It is a increasing function. Okay, it is an increasing function. We will see in the later presentations what does it mean while solving the problem, how it will increasing. So remember that the distribution function is, okay, it is increasing, also called as monotonically increasing. Monotonically, it is an increasing function, right? That is the meaning of it actually. And similarly, there is, based on this particular, you will have another important relation property. Otherwise, this is very important property. The fifth one is that, so if the probability is defined for the event, I mean x1 is less than capital X, right, is less than or equal to small x2. This is equal to, okay, this is the event basically. This is the event. If you write something in this particular bracket is called as an event. Now this particular event, in this the random variable x has two possible values. That possible values are lies in between x1 and x2. x1 is less than capital X is less than equal to x2. Then the corresponding distribution function gives rise fx of x2. You have to note on this minus f x of x1. That is the meaning of it. If you take the probability like this, probability of x1 is less than capital X is less than or equal to x2, then correspondingly if you write in the form of distribution, the fx of x2 comes first. Fx of x2 minus fx of x1 means the probability distribution function of x2 minus the probability distribution function of x1 comes like this. These are the very nice and beautiful properties of a probability distribution function. Clear? I think you have understood about this distribution function and the concept of the random variable. We have seen the properties of the distribution function also. So these are very much required, very much useful, right, in solving the problem actually, right? So I think we will finish off this presentation here and we will continue with the subsequent information of this particular, continuation of this distribution function in our next presentation, right? So thanks for watching and have a good day.